Fundamental Theorem of Calculus Part 2. It's basically just the definition of a definite integral, and you take the antiderivative of the integral from a to b and you evaluate it at f of b, which is the upper limit, minus f of a, which is the lower limit, which you get from looking at the original integral. This is the free response question. Part: as the pot of tea cools, the temperature of the tea is modeled by a differentiable function h for 0 when t is greater than 0 but less than or equal to 10, where time t is measured in minutes and temperature h of t is measured in degrees Celsius. Values of h of t at selected values of time t are shown in the table above. Part A. Use the data in the table to approximate the rate at which the temperature of the tea is changing at time t equals 3.5. Show the computations that lead to your answer. So here's part A, and we are looking for the rate at which h changes, so at time 3.5. So that means h prime of 3.5 is what we're looking for. The rate of change equation is f of b minus f of a over b minus a. And in this case, we look at the table at 5 and 2 because those are the two values which 3.5 falls between. So b equals 5 and a equals 2. So you plug it into the rate of change equation, h of 5 minus h of 2 over 5 minus 2. And that simplifies by looking at the chart. You find 52 minus 60 over 3, which equals negative 2.667 degrees Celsius per minute. Part B asks, using the correct units, explain the meaning of 1/10 integral from 0 to 10 h of t dt in the context of this problem. Use the trapezoidal sum with the 4 subintervals indicated by the table to estimate 1/10 the integral of 0 to 10 of h of t dt. So 1/10 integral of 0 to 10 h of t dt is the average temperature of the tea in degrees Celsius over the 10-minute period. A trapezoidal sum, you take 1/2 base 1 plus base 2 times the height. So the height's going to change in every trapezoidal sum. So 1/10 the integral of 0 to 10 h of t dt is approximately, we have to include this 1/10 here because it's the average temperature. So it's 1/10 times 1/2 base 1 and base 2. So you look at the chart, base 1 is 66 plus 60 times the change in time, which between these two is 2. Plus 1/2 times 60 plus 52, which is the next interval, times 3, the change between those two. Plus 1/2 52 plus 44, once again up here, times 4, the change in the time. Plus 44 plus 43, up here, times 1/2, and the time is just 1, so you don't need to write that. So it simplifies down to 1/10 times 126 plus 168 plus 192 plus 43.5, which simplifies to 1/10 times 529.5, which gets you to 52.95. Part C asks to evaluate the integral from 0 to 10 of h prime of t dt. Using correct units, explain the meaning of the expression in the context of this problem. So in this problem, the integral from 0 to 10 of h prime of t dt is asking for the total temperature change, because as we know from above, h prime of t is the rate of change that the temperature is changing at. So because of the fundamental theorem of calculus, we know that the integral of h prime of t just means h of t minus h, which would be h of b minus h of a. So in this case, it's h of 10 minus h of 0. So you can look at the chart and find your values at these times. So h of 10 is 43 and h of 0 is 66. So 43 minus 66 equals negative 23, which means that the temperature has dropped 23 degrees Celsius in the 10 minutes from t equals 0 to t equals 10. And finally, part D asks, at time t equals 0, biscuits with temperature 100 degrees Celsius were removed from an oven. The temperature of the biscuits at time t is modeled by a differentiable function b, for which it is known that b prime of t equals negative 13.84 times e to the negative 0.173 times t power. Using the given models at time t equals 0, how much cooler are the biscuits than the t? So first we need to find b of t. So we need to find the temperature of the biscuits at time t equals 10 minutes. And we know that b prime of t equals negative 13.84 times e to the negative 0.173 t. So b of t equals 100, because that's the original temperature of the biscuits, plus the integral from 0 to 10 of b prime of t dt, which would give you the total change in the temperature from 0 to 10 minutes. So you get 100 plus integral of 0 to 10 of b of t, b prime of t, which is this, and solved it equals 34.18275, and it asks how much hotter the t is, so you have to find h of t minus b of, or h of 10 minus b of 10, and we can just look at the chart from above for h of 10, which is 43, minus the b of t that we just found, which is 34.18275, and you get 8.817 degrees Celsius. So this means that the biscuits are 8.817 degrees Celsius cooler than the t at time equals 10.